button times out after 10 minutes. So sometimes it's one of those things you definitely don't want to miss. And something happened. What says it's being sent? I think we're okay. Okay, I think we are in fact recording. Welcome back, folks. I did just double check that. If something ever happens to a recording, I mean, that is pretty unfortunate. Worst case scenario, I might pull in a link from a video that was done in a prior semester, but that's a pretty rough patch job. So we'll try to make sure each of the classes get recorded. Awesome, I'm glad to hear that, Emily. I'll try to make a notification about that for the folks after the 2 week period, especially. But for the moment, if you don't quite have the $117 to register for WebAssign after opting out of the book bundle program, then no worries for just waiting for the end of the 2 week period. But welcome back, folks. First class was mainly just introducing the course. There's lots of things that go into kind of a interesting in-person versus fully online section using tools like WebAssign to learn calculus. So we had lots of great questions. I appreciate everyone's engagement. And well, pretty much this is what the experience is going to be every time we come back. We'll have some doodles just drawn out here, some boxes to say where we're at, maybe a couple formulas and ideas as refreshers. And then after taking questions for the class, after the announcements, we'll just jump back where we left off on the prior notes. We didn't get too far, we're still in. But other questions or comments at the moment? Okay, well, it's always a kind of a slow start on week 1 for this class. We really start getting in a better pattern, a better pace after week 2, 3, and so on. So I'd say, looks like most of the class is registered for the WebAssign. If you have not yet done that, this is the link to get started, to begin looking into the textbook and into the homework. I'll be going back into WebAssign here and there, particularly next Tuesday, once we've had a chance to really work into that system over the weekend, to point out different things, how to request extensions, how to get extra help working with the textbook, and so on. But any questions or comments whatsoever then before we go back to section 2.1? Okay, well, let's get started. Welcome back, folks. We didn't do a whole lot of calculus last time, but we did describe the big major calculus problem that we want to solve. If we have a curve like this, which could represent any kind of physical quantity, it could be like in this situation, this is a distance away from a starting position where we're measuring time in hours, distance in miles. In this situation, if we can find the slope of that line right there, it's of vital interest. That slope m is going to be rise over run. It'll be change in distance over change in time, but that's just going to be the speed or velocity in miles per hour. So solving that is a pretty interesting, has a pretty interesting connotation to physics already. But like we mentioned, this could be a population model, this could be economics, this could be something else in medicine, maybe the rate of a drug in the bloodstream and so on. And if this was the, say, concentration of a drug in the bloodstream, that slope would tell us the rate of change of that concentration after maybe ingestion of a tablet of something of that's nature. So let's now turn to the problem of how are we going to solve this slope? It'll take us a little while. We're going to solve and find that slope in chapter 3, and everything we're doing in chapter 2, all this machinery we're going to learn about, limits and continuity, is to find a way to compute that slope exactly. Well, let's get started then. Limits are kind of a weird topic. That's why we do spend a little bit of time saying why we care about them, because it feels like we're getting lost in the weeds a little bit in chapter 2 before we come back to this picture, which we definitely will in chapter 3. And starting off the discussion of limits is kind of rough because it's a very dense statement mathematically. One thing that's kind of interesting about calculus is sometimes the algebra gets kind of gnarly, so we'll take our time reviewing algebraic methods. But the other thing that gets a little bit heavy is the notation. This little symbol here by the red dot is saying a lot of things all at once. So let's break down what this is trying to say step by step. We'll say, suppose f of x, a function, so that's much like the function in the example 1 down below. Here is y equals f of x. Suppose that that function is defined when x is near some number of interest, a. That means it's going to be defined on an open interval that contains a, but it doesn't actually have to be defined on a outright. It could be undefined. It could have some little weird discontinuity like you see here. But if it's defined around a, we're thinking of 1 being the a in this problem, then the limit of f of x as the x input gets closer and closer to the value a will equal L. That's what this all is saying together, but what it means is this is going to be a true equation. If we can make the function values f of x as close as we like, arbitrarily close, to the limit L by taking x to be closer and closer, sufficiently close enough to a on either side, but not necessarily equal to a. We're not concerned about what happens at a itself. We only care about what happens nearby. So there's really three things going on here. There's the definition in words, kind of an informal definition. There's the symbols, the actual notation for the limit as x tends to a of the function f of x equals L. And let me change my color coding around a little bit for that y equals f of x. I want to maintain the blue and green that we see here on the problem below. And then there's the actual graph that we see here, trying to see how this all comes together. We're going to look into limits in two kinds of ways. Section 2.1 is all conceptual. If you can see how a limit looks visually, what it's really trying to say, it makes the algebra, doing it without a graph in the very next section, 2.2, come together a lot better in our mind. So think of this is the mental picture for the next section. So we have a function f given below. It's kind of a weird function. It goes down in a linear kind of way. Then there's a hole in the graph right here. One little isolated point, and then when we go to the right of one, it starts increasing gradually in a certain way. It doesn't look quite linear over here, but that's the whole function. We'll use the graph to compute two values, the function value f at 1, and then the new thing, the limit as x tends to 1 of f of x. So let's work this out slowly and visually. F of 1's not too bad. This is really just a review of pre-calculus topics, working with graphs. If we were to calculate f of 1, really all we do is we go to the input value 1 that we're evaluating in function notation. Here's 1 on the graph. Then we move vertically, either up or down, until we hit a point on the graph of y equals f of x. And it hits the point right here. There's no function value at 2. That's why we emphasize the open circle to say there's an actual hole in the graph right there. The function value takes a value of 1. The output is 1 here, and so we say f of 1 is equal to 1 itself. So that's just an ordinary function evaluation. Any questions with that review topic there? Okay, what's important about this particular example 1, the reason we're starting right out of the gate with this example, is the value of the function f at 1 is not necessarily going to be equal to the limit. They could be equal, but that's no guarantee. It just depends on the function and the value that we're working with. So now this time, following the color coding here, we're going to take the limit as the value x tends towards the value we care about, a. In our problem, a is 1. So we're thinking of x values being on either side of 1, getting closer and closer to 1, as a red dot is, but never equal to 1. Don't forget that part there. We do not care about the actual a value, 1 itself. It's all about around 1. We'll take the limit of that function, f of x, and see what it'll come out as. It's got to be some number on the y-axis, some height, so that you get closer and closer to that number as x itself gets closer and closer to 1. That's a highly visual thing, so let's really zoom into this graph. X getting closer to 1 could mean maybe you're right here at this value. You would go up, hit the graph, and it would output some value here, maybe 2.8 or so on. Around 1, we're interested on both sides. So we're also thinking, what happens if we take the limit from the right end? Maybe a little bit closer. The limiting value is saying, what is the height of the curve y equals f of x as you get closer and closer, as close as you want to 1. So for right here, say about 1.5, we would go up, hit the graph, output some value. Looks like just by a fluke, it's pretty close to the same. Let me do a slightly different value so the picture looks a little bit better. Let's get even closer to 1. So we're about maybe 1.25. We'll go up, hit the graph, and now put a value that's slightly lower, somewhere right around here. But that's not the value of the limit. The value of the limit is what these arrows are getting ever closer and closer to. The closer and closer we take an input value to 1. So let's erase some of these so it doesn't get too busy. Let's imagine we're really zooming in on this now. We're taking a value maybe like a 0.9. When you throw in a 0.9, you're hitting the graph here, you're outputting a value right around there. You'll notice all the values are starting to get lower. The closer and closer we got to 1 itself. F of 1 is, oh, that's way over there. F of 1 comes out as 1, and that's absolutely not the limit. We're not getting anywhere near 1. We're getting closer to something else. Any volunteers to say what that something else might possibly be? Let's do an even closer one to see if we can get a feel for that. Remember with the limiting process, it says you can get as close to 1 as you like. You just can't put in 1 itself. If you put in 1, that's a function evaluation. If we want to get to even closer and closer to that, maybe it looks like this now. So imagine that dot is at, say, 1.001, as close as I can make that to 1 visually without it looking dead on like a 1. We go up, we'll pass through that value because we didn't plug in a 1 at all. This is like a 1.001, recall. So we don't get the function value of 1. We just keep on going up and up. Pretend that's a vertical line until we hit maybe right around here. And now we're even lower. We keep getting lower and lower, but not without bound. We're never dropping down there. So it looks like there is one particular number we seem to be really approaching. Oh, I missed some chat. Sorry about that. Emery and Haley says, looks like we're getting close to around a 2. And that's absolutely right. Visually on this graph, the limit to this one is 2. You can imagine if you printed out your notes or if you have a digital tool, you can really just draw this out and see experimentally, does that seem about right? Take a really close value, draw to about here, outputs ever closer and closer to 2. The closer and closer the input value is to a 1. So that means the limit in this whole process is 2 itself. So we did it, folks. That's the idea of a limit. What is the function getting closer to? 2 in this case, as the input value gets closer and closer to a 1. So in short, this is saying the height of the curve f of x is approaching L. And we can get as close to L as we would like by making x sufficiently near A, but not equal to A. Throwing in A inside of this process in a limit is a function evaluation, not the limiting process. So this part is easy to really miss in the reading. That's why I try to overly emphasize it. The function doesn't even have to have a value at A. It could have been totally undefined here, no solid dot, and yet the limit will still exist. So this is the major punchline with what we're doing in these notes in 2.1, a conceptual view of limits before we try to do them computationally by hand. Any questions or comments at the moment? Oh, sorry, I missed a chat. Haley says, would it have to be slightly above or below 2 since it can't hit a 1? Turns out it wouldn't be below 2 on this one. in this particular problem, it would have been exactly a 2. So Trey says, does it matter which side of the line you start from? Actually, it really does. For this particular limit A, you have to be approaching 2 on both sides at the same exact time. If on the left side you approach 2, but yet on the right-hand side you approach 3, this limit would not exist. It would be undefined. We would only have single-sided limits that we'll see later on. Other questions about that so far? Okay, well, this can't be our only problem on this topic because it is pretty tricky. So let's turn this to just another highly similar kind of problem. 3 functions now at the same time. Well, it's 3 functions, but notice how similar they all look. This is the function x squared minus 1 divided by x minus 1. And if you had a graphing calculator nearby, you might have told yourself, that looks kind of funny. Why is there a hole in this graph? Well, you can't plug in 1 into the function, right? If you plugged in 1, you'd be dividing by 0, and the whole thing is undefined. And the way your graphing technology works in almost all situations is we put in f of x equals x squared minus 1 divided by x minus 1. Most graphing technologies is going to draw a line that goes like this. Makes this graph look a bit like a lie until you look really close. What actually happens, let me get the scale about right, so it looks similar. What actually happens around 1, if you go right here, notice, there we go, let me try to hold it there. That's really hard. I drank too much coffee today. There we go. The technology does put an open circle to emphasize there is a true hole in this graph. So it's kind of a weird problem. There's a hole on this one, f of 1 is undefined. The function g of x is a brand new function, something totally different. This one's considered to be a piecewise function. On this piece, where x values are not equal to 1, it's the same graph in part A, f of x. But we decided to define g at the input 1. At 1, it's going to come out as 1 itself. So this whole line right here pretty much just does that. It puts a dot somewhere. So now the function's defined. Well, that's a pretty bizarre function, you might say. If you were going to define a function and you put a dot here, what an arbitrary choice that is. I think most people would want to plug the hole, right? That just seems like the natural thing to do. If there's a hole in the graph, make continuity happen by plugging it in. And that's what h of x does. H of x is just x plus 1. We put a solid dot here to just emphasize it's not only defined there, but there is no hole in the graph as well right at that point. In either one of these cases, we want to compute the limit as x tends towards 1 for all 3 functions. Well, those are our graphs. Let's give this a try. On the first one, f of x, the limit as x tends towards 1 on the function f of x here, I'll just write f of x, but you could write in x squared minus 1 divided by x minus 1 if you prefer, is going to be equal to, well, based on what we did in the last problem, looks like it's a 2 again. Would you all agree? Awesome, thanks for the input, Haley. Yeah, it looks like this one should also be a 2. Let's draw some lines in just to convince ourselves. If we were, say, right here, we go up, hit the graph, and notice we're below 2, kind of a little bit different than the last problem. But if we go over here, maybe a little bit closer, go up, hit the graph. This time we're above 2. Try to draw it a little bit closer, but it's hard to get really, really close on these by a hand sketch. So sometimes we're below 2. On this end, we come out above 2, but in either case, another way to visualize this is if you're on this end of the curve, your x values are getting closer and closer to positive 1. But as you move that x value closer and closer to 1, the y values get closer and closer to 2 from below. we can't put in this value. We can't plug in 1 exactly. As we come in from this end, we're above 2. X is above 1, but as X gets closer and closer to 1, we start marching down closer and closer to 2 at every step. So either draw the arrows showing the inputs going out, or imagining a dot following, or maybe a finger following along the curve. Either way we see it, the limit comes out as a 2 on this one. Well, that's 1 down. Haley says, so in other words, find the y value of the limit, or would that not work in some cases? Let's see. Finding the y value of the limit, pretty much that's what's going on in this one, but you're right as well. In some cases, we can't just take wherever the hole is, grab the value to get an output. In some cases, the limit is not going to exist. So that's going to be when we look into the so-called single-sided limits. I'm going to draw a particular graph where we can't just read it in the same kind of way like we did before. Does that make sense with that comment there, Haley? Awesome. Okay, let's try out another one. So what's kind of confusing about this problem is when you look at this limit, when you're following the curve, you're getting closer and closer to a 1. The height of the curve is also getting closer and closer to 2. I mean, these are pretty similar curves. Right at 1, it drops out, gives an output of 1, and that's through this part right here. So while it is true that G, let's write as just a comment like this, G of 1 equals 1, that's not the value of the limit, that's a function evaluation. If on this problem we take the limit as x tends towards 1 of the new function, g of x, this limiting value is still a 2. That new defined point right there, it's just a distraction, really. It's easy to kind of mislead our eyes because we're a lot more used to function evaluations like these through the graph, but the limiting process is different. It's asking the question, what are you actually approaching as x gets closer and closer to 1, but is not ever equal to 1 itself? So we don't actually put in a value here to output a 1. We're still approaching 2 on this graph. So that's the limit on that one. And this one's like the world's nicest graph, right? There's no holes. There's no point that's undefined like on this one. There's no loss of continuity where if you drew this, you have to take your pencil off the paper to draw on that dot and then keep going. That's our loss of continuity. This one is just a nice, clean, continuous curve. Nothing bizarre happens. That point is just emphasized to compare with the other graphs. On this one, you could pretty much just say the limit as x tends towards 1 of h of x is directly equal to 2. And this one feels like familiar algebra. It works out on this one, just plugging in a 1 here and coming out with the 2, but that does not work on every single function. It depends on the function in particular. Well, that's 3 fast kind of limits to see what can go on with these slight changes to one graph, the 3 different functions. Any questions at all, folks, practicing with this one? Okay, what's kind of interesting algebraically is part A, the function f of x, and part C, the function h of x, are really, really strongly related. This is something that we take for granted massively in algebra. We saw a function like f of x, say in an algebra setting, we would often do the following. Orange is just going to say this is just an additional comment to go along with the example, not part of the solution whatsoever. But if we took f of x as x squared minus 1 over x minus 1, some people in class might have had the mental urge to say, factor that numerator where the red dot is. It's a difference of squares. It factors as an x plus 1 times an x minus 1. And factoring is a great way to simplify a rational function like that one. You can now do a cancellation. That part's gone. It becomes the function x plus 1, which is equal to h of x. But there's, a weird thing that happened here. That equality is a lie. It's one of those weird white lies that happens in mathematics over and over again that we kind of just skim over so that we don't have to write this statement every single time. This equality is only true when x is not equal to 1 itself. Because once again, you can't plug 1 here either. You'd be dividing by 0. Even if it's 0 over 0, you've got a problem of undefined. You can plug 1 here. So the whole algebraic topic of taking a rational function like this one, simplifying it, meant what you were really doing is taking a hole in the graph and plugging it for a function like this one. Simplifying is plugging a hole. That's kind of a weird thought altogether. Haley says, why does h of x have a limit even without a hole? Well, the idea with the limits is the value of 2 for a limit is just what the curve is getting closer and closer to as x itself gets closer and closer to 1 without ever even putting in 1 itself. So even without a hole, we can ask and answer the question, if you're really close to 1, say here, what is the function value getting really, really close to? It will still be a 2 on these curves, whether you're above or below. The closer and closer you get, the closer you get to the value 2 itself. So with a hole or not, you'll still have a value for a limit on this one. Does that make sense with that question there? Awesome. So the thing that's weird about limits is oftentimes we're looking at limits in these kind of weird pathological cases where there's holes in graphs, like this weird hole right here as well. But sometimes when you take the limit, there doesn't have to be a hole. And you'd notice that that's kind of interesting how this is the first function, that h of x function in part C, where something new did happen, like you were mentioning there, Haley. We have that h of 1 is also 2, and because these match, this means h is continuous at x equals 1. And whenever we have continuity, it turns out the function evaluation is exactly the same as the limit. We love continuous functions because it means doing the limit was just a matter of plugging a 1 in there really and getting a 2 out. But not all limits give us continuous values whatsoever. So that's why we need to see it from this end as well. What happens when there's a hole in the graph? And that's very relevant to what we want to do in finding the slope of the line right up here. Because when we go to write the slope of this line based on 1 point, it's kind of like we have a hole in the graph. We'll be dividing by 0 if we just use 1 point with the slope formula. So we're trying to find a way around that altogether. Well, other questions or observations at the moment? Zoom out to see that whole picture. Okay, so sometimes limits are kind of unfamiliar. The function value on this one is undefined. The function value on this one is a 1, but it differs from the limit. That's a discontinuity. But on this one, suddenly the weird one, because it was so nice, the limit is 2, same as the function value, which means it's continuous, but visually that just means there's no hole in the graph. You can draw this curve without ever lifting up your pencil. Well, I mean, it does go infinitely in both directions, but you could imagine you wouldn't have to actually lift up your pencil to draw just this segment. But there are other questions that were raised in the chat that suggest this isn't as nice as it could be. There are even weirder graphs to consider, weirder things that happens with limits. Limits don't always even exist. Sometimes a limit is pure on undefined altogether. We can't put a number down because the function is just that weird. That's our next example, so let's take a look at it. So the limit that we discussed didn't have any new symbol like these two have. Let me make this even a little bit larger so we can really see that symbol. Where did that go? Here we go. Okay, The last limits we were looking into didn't have any symbol like that negative sign there, or any symbol like that positive sign there. We were looking at double-sided limits in a sense. Now we are looking into a single-side limit. If we put a negative sign here, we're talking about the limit of the function f of x as x approaches a like before, but it's approaching from the left. X is always smaller than or equal to, strictly smaller than a, but not actually equal to it, strictly less than. So here we're approaching a from the left. Down here, we're approaching a from the right. And let me just hide that for the moment so it's not a distraction. Let's draw a graph to convey what these limits might look like. This will be just a freehand sketch. So here's a random problem from my imagination. Kind of going to be a weirder function, weirder than we've seen all day. Let's put down a scale so we can make it more concrete. Let's go -1, -2, 3, +1, 2, 3, 4. I probably didn't need the 4, but it's there. The value that we're interested in will be a 3 in this case. So we'll be taking the limit as x gets closer and closer to 3. But this is going to be approaching from the left. We'll take a new limit as x gets closer and closer to 3, but we'll approach it from the right. X will always be larger than 3, in other words. Now let me draw the actual function. Let's put in a y scale. You mean, say, this one here? It's kind of like this one, except what I'm going to do is take this piece and just move it up. So there's going to be a huge break in continuity. This discontinuity is not too major, right? Because it's just one point removed that caused a loss of continuity. But I'm going to severely destroy continuity by moving this entire branch of the function up by the same amount, essentially. Let's do just that. It's going to be at 3 where all the action is. Let's make that look kind of familiar. So I'm going to approach all the way down to, say, this point right here. Let me put in an open circle. The curve is going to come down in kind of a linear way, like that first example, at a height of 2. But what happens when we move to the right of 3? Something totally different. Let's say we move this branch upwards. So this is at a height 3 now. It's got to be vertically right above my little open circle. And it's going to do this. I'll put a little arrowhead just to convey it's going forever in that direction and that kind of pattern. And it's going to the left forever in that direction. But as soon as it came down to 3, something kind of major happened to this graph. Now when we go to take a limit, like the limits we did just before, it doesn't work out the same kind of way. That limit turns out to not exist, and we can kind of see why. If you're approaching from the left, this is what it looks like. The function values are dropping down, down, down to a height of 2. And you can get as close to 2 as you would like, but if you're coming from here, the values are going down, 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 but to a height of 3. So on one end, your limit looks like it's a 2, but on the other end, it looks like the limit is a 3. And that's no good for us in mathematics. If there's 2 different answers to something we're expecting a unique answer to, well, that's what the limit is, not what the limit is all about. There are concepts that do work like that in mathematics, but they're vague and interesting topics. This has a unique answer, one particular number. But there is still a particular limit that does exist. Let's do a left-hand limit and a right-hand limit and look through these definitions one more time. If you write down the limit as x tends towards a, but you specify a direction you're going now, not a double-sided limit, you're only approaching from the left-hand side. That looks weird. It's in the exponent position, a superscript with a negative sign. That means we're not negating a, we're just saying pick a direction to approach a from. Oh, and let's make this concrete. I want to use the actual function value 3 down here. A is going to be a 3. So we're not saying -3. We're just saying we're following the curve down towards 3, but from the left of the function f of x, like we did on those other limits. Because there's one direction, we can put an answer to this one. This one does exist because we said you're only looking at one side. We're getting lower and lower till we get closer and closer to a height of 2. And that means this limit is 2 right here. So from this end of the graph, we get that particular limit. Does that make sense to folks at the moment? Okay, let's read through the definition. It says, this limit comes out as a 2 Ava, oh, sorry, not too sure what happened there. Might have been just a cat might have walked across the keyboard. Not too sure, but yeah, no worries at all. Okay, so reading through the definition, it says, as we take the limit of f of x as x approaches a from the left or approaches 3 from the left, it's going to be equal to L. Our L value is 2. If we can make the values of f of x arbitrarily close to L by taking x sufficiently close to 3 in our problem, but always less than 3. It can never be 3 itself, just like on the prior limits. And that's what we saw visually. If we turn it all around on this one, it just says the limit of f of x as x approaches a from the right-hand side will take a limit L. If the values get closer and closer to that number L, as x gets closer and closer to a, but it's always greater than a. In other words, it's approaching it from the right-hand side. This limit would then look like this. Take limit as x approaches 3, but we're only going from the right-hand side using this limiting process, which means this left-hand side, and for our purposes, it just doesn't exist at all. And you could really emphasize that if you'd like. Sometimes this seems like a kind of a strange, silly idea, but it's pretty helpful actually. Put a note card down, it's a little bit easier to see the limit, because if you're going in from the right-hand side, this is the only piece of the curve that you actually care about. And we're getting closer and closer to a value. I kind of need my axis though. That's trick has its limits. We're getting closer and closer to a height of 3 on this function. So the limit as x tends to 3 from the right of f of x was meant to be dead on at height 3. Well, those are two interesting single-sided limits. But what it means is, here's the big punchline, the limit as x tends towards 3, that's a totally different kind of limit. Again, the notation is dense in calculus, and limits are no exception. And if you change one tiny, tiny little symbol, you've changed everything about the problem and the answer that you're going to get. The negative sign had a value of 2, whereas if we did a positive sign, we got a value of 3. And if we don't put any decorations around it whatsoever, we mean approach 3 from both sides at the same exact time. There has to be one exact answer for equality to even make sense, but there's not. The value you get just depends. Are you on the left or are you on the right? It's either a 2 or a 3, but we can't say that for a limiting process. We can't say the limit is either 2 or 3. It would make it seem like we're just not sure. This one does not exist outright. It's a limit that you could write down on paper, but there's no number you could put down, no single number you could put down here to equate to it and make a true statement. Since does not exist comes up a lot in calculus, there's a big acronym for this. The shorthand is DNE for does not exist. And that's something you'll type in occasionally in the homework as well. DNE is going to come up here and there, even in the next chapters. It seems kind of abstract when you see it. So when you see DNE, just think does not exist. And this is just a context-sensitive way of saying undefined, really. Does not exist is just saying it's undefined in the context. We were taking a limit, but that limit did not exist. Well, we've looked into three kinds of limits: the double-sided, the one that didn't exist in this particular graph, and the single-sided limits. Those did exist, they have values. Any questions with either of these so far? Okay, so functions are weird. I haven't done anything too major, and already we're seeing pretty strange behavior when it comes up to functions. Other questions you might have is, can you put a function down and a number where the limit doesn't exist at all, but it isn't because of a break in the graph? We can put down a function that's continuous, yet the limit doesn't exist. And one of those functions might look like, say, this thing. Oh, that's was a miskey. Let me close the hat. Let's let f of x be something like sine x. We're not going to do a lot of trigonometry in this class. It's not part of the prerequisites. But if a weird example comes up and it just pays to put down a trigonometric curve, we'll do it just for the sense of emphasis on how weird these functions can get. Instead of an x, if you put in a 1 over x, something kind of weird happens here. Imagine trying to take the limit as x tends towards 0 on this thing. You would try to get closer and closer to 0, but this is oscillating more and more the closer and closer you do get to 0 until you get to this region. It's moving up and down so fast without a loss of continuity that there is no number you can actually put down. The closer we get to 0, the more it bounces up and down. It's not approaching one single number whatsoever. For a limit to exist, either a single-sided limit or a double-sided limit, you're approaching something like on these problems. It's getting closer and closer to 2 on either side, so that's why we said the limit is 2. But on this one, it's just pure madness. The more you zoom in on this, the worse it's going to look, and the technology is just going to break after a while. It's just going to get to the point where Desmos is just putting red shading now. It can't even tell you how fast it's oscillating near 0. Some weird kind of singularity is occurring there. But these kinds of limits did exist on the single-sided, just not the double-sided limit. And one nice theorem to finally show that ties all this together is we get to say a limit like x tends towards a. This one is the so-called double-sided. It will exist and take on a limit of L if and only if the single-sided limit, the left-hand limit and the right-hand limit both exist and both equal exactly L. So if you did a single-sided limit with 2 here, and if this one came out as 2, well, that would mean the whole curve had to come down like that, like our first example. But that would mean the limit does exist, and it would be the same value 2 as well. So if the single-sided limits exist and they take on the same value, so does the double-sided limit. These two are the single-sided limits. So far we've looked into some pretty interesting extreme behavior functions, and it keeps on getting weirder. We learn a lot about functions in pre-calculus settings, how to graph them, different classifications of functions, and they hint at limits a little bit when they talk about vertical asymptotes and horizontal asymptotes. But this information is probably new so far, but we are getting into some familiar territory next. Next, we're going to look into vertical asymptotes and how they relate to limits. Any last questions at all before we take a look into the next concepts? Okay, so you'll practice problems pretty similar to this in the WebAssign homework. My goal is pretty much to always, when I select the topics in WebAssign, I build my notes to try to match it up. So if anything looks weird on the problems as you go to solve them, like I mentioned before, don't hesitate ever to hit the Ask My Instructor button. Always be very happy to engage with you. And people have already taken my word at that. Some people have already asked questions and I've been able to work through them and help people out. So when you get starting with your homework, anything that looks a little bit weird, give it a try. If it's not working out or if it just seems kind of crazy, I'll be happy to help out. Let's move down to, I guess this is not the new concept yet. Sorry about that. The new concept is down here where we output infinities. I forgot I made a good choice to put down just one more problem where we're going to put everything we learned together and evaluate just a slew of limits. Sorry for the slightly fuzzy, low resolution picture. I'm going to double check my notes and try to correct those, make them a little bit more high quality. Instructions say, use the graph of f. Here's our graph. It comes in two different pieces like the last graph we drew, but we think of this as just one graph overall. It's just a pretty messed up looking function. Has a big jump here, jump discontinuity, and a little hole here, a little removable discontinuity. We'll use the graph of f to state the value of each quantity if it exists. If it does not exist, we'll give a really fast explanation. It doesn't have to be anything too major. And just so that we have it, let's bring this tool along with us. We'll just tuck it away here for the moment. Okay, so here's our graph. We're going to evaluate several limits. Let's just go top to bottom, or left to right, top to bottom. But we have to be careful on every one of these. It's a good idea to just really stare at the notation as you see it to see what exactly is going on, because this one is a single side limit. We're approaching 2, but we're approaching 2 coming in from the left. We follow this curve, and we see what does the height get closer and closer to as we get ever near 2, but not equal to 2. This one has a solid dot, but that doesn't make the limit not exist. We now see that as we get closer and closer to 2, looks like the height of the curve is getting closer and closer to a 3 on this one. Does that make sense to folks on that particular limit? Okay, let's try it out again. Any volunteers for what this limit should come out as? The limit as x approaches 2, now for the right. Awesome. Yeah, this one is going to come out as a 1. Good call. Again, there's lots of ways to visualize this. Sometimes I get in a good habit of just using my finger, have it approach 2 if I had this printed out. Maybe it's an exam problem. I'm only going to be on the right-hand side of 2, but as I get closer and closer to it, the heights drop lower and lower and lower. They'll never hit 1, but you can get as close as 1 as you would like by just making the value of x get closer and closer to 2, but always larger than 2. So this limit comes out as a 1. Now that makes this limit kind of weird. Suddenly, this one is a double-sided limit. Haley says that since the number is different from the left and the right, it should not exist. And just like Emma said as well, absolutely. This one is a DNE for does not exist, or you could say undefined. Let's go with just an ordinary DNE, because that'll be a little bit more familiar in the textbook reading and the homework as well. It said explain why. So if you saw this in an exam setting, you don't have to do anything too major here. I would personally write does not exist. The left and right hand limits are not equal. On one hand, you get a 3. On the other hand, you get a 1. So that's an automatic does not exist. In fact, you might have already been anticipating that. If there is a big jump in the graph like that, it's an automatic does not exist for the double-sided limit here as x tends to 2. Single-sided limits exist on this one, but overall, that one did not. Here's another tricky one. We haven't done a lot of function evaluations, but we've done a few so far. Anyone see what f of 2 equals, on the other hand? It's kind of a different graph from all the other ones we've seen so far, right? Usually when we did this, there was like a dot isolated somewhere else, but this one is slightly different. Yeah, absolutely. Haley, this one will come out as a 3. Good call. Pretty much the thought is always look where the solid dots are in the open circles. Take the input value of 2 and just imagine you started at 2, pass through that one because it's an open circle, but stop wherever the dot is. It might be right as an endpoint on a graph. It could be floating around, like say on this problem. The function value is a 2 here, or excuse me, a 1 here for g, so it doesn't have to necessarily be like on those last examples. So here, we land at a solid dot because it's at height 2. We'll say that f of 2 is 3 on this one. Now, it gets even weirder because if we try to do a similar thing, a function value, let's skip around just a little bit and ask the question, what's f of 4? Well, that one is a pure undefined. If you said does not exist, that's all right as well. But in the context of a function, we would usually say undefined. That's because there is no solid dot whatsoever on the vertical line that goes through 4. There's no dot defined down here. There's an open circle right over here. So f of 4 itself, we wouldn't even write equals. We would just say outright undefined. But that goes back onto the topics we looked into on the very first example. The function value might be defined. That's example 1. It could be undefined. That was example 2, part A. But that has no relevance to the limit. The limit can still exist. Let's take a look at it. If you're approaching the function value of 4 on this limit, on the left, we get higher and higher and higher, closer and closer to a value of 4 as the outputs. But that's just on the left-hand side. For the limit to exist, it has to match up on both sides simultaneously. But we're kind of seeing that, right? If you start on the right-hand side, now we're approaching 4 from the right. It starts below, looks like it actually goes a little bit above 4, but then comes back down. Starts to get closer and closer to 4. Since we approach a height of 4 on either end, this limit does exist, and it takes on a value of 4 itself, despite the fact f of 4 is undefined in the very first place. But in the definition of the limit, it said it pretty much doesn't matter what happens at 4. It's all about what happens around 4 on both sides simultaneously. Yeah, good call. That would have come out as a 4. Sorry, I think I missed that chat just a bit there. But we did it, folks. That's the kind of a big review on this one. Problems like these, because we're spending so much time on them in class and the homework, they could be a bona fide exam 1 question as well. So you'll practice this in the web assigned system as well as in the lecture notes. We're not going to assign a quiz on week 1 because there's a lot of work just getting started. But I also like to give a hint on quizzes as well on what would qualify as really big exam questions. Well, let's now finally move on to the next topic, like I mentioned. What happens when we're looking into vertical asymptotes? And limits don't output a number, but things like infinity or negative infinity. So that'll be our next one to take a look into. And like before, with the single side limits, this goes really well together with just drawing a big plot. Let's just draw something kind of random. We'll see how these definitions work, because in my opinion, just reading the definition and understanding it is like impossible. You really want to conceptualize it by drawing something. Then we'll do what we did just prior all over again and review those topics through another problem like this one. So here's our next set of technical definitions to get through. We have affinity outputted on this one, a negative infinity outputted on this one. So we have to make sense of what's going on in either one of those cases. It says if f is a function defined on both sides of a, except possibly at a itself, then we write the limit as x approaches a from either side of the function f of x is infinity, and it means the values of x can be made arbitrarily large. That means as large as you want. F of x can reach a number of a million, a billion, a trillion. It could reach the number of 10 to the power of a million. whatever number you like by just taking x close enough to a as you would like to make the function values high enough, but not equal to a. So this is the statement that just keeps on getting repeated. In the limiting process, it's not about what happens at a, it's about what happens around a. So that statement is duplicated pretty much every time we define a limit in this way. So here's the graph that's going to go along with this one. The function values essentially blow up in the positive direction for this limit. They also blow up, but in the negative direction going down in this limit. But what that would actually look like on a graph is about like this. Let me move, say, 4 paces to the left here. Let's go 1, 2, 3, 4, 5 to the right on this one. So again, just a randomly generated example. This could be a potential exam question, but I'll try to actually make prettier graphics, computer graphics, rather than hand-drawn. And the graph could look something like this. The way we're going to get f to tend towards positive infinity or a negative infinity is if there is an asymptote. So let's just start by drawing those asymptotes. Asymptotes are vertical lines, and so they have equations. This one will be the equation. X equals -4 gives you that vertical dashed line. This one's the equation x equals +5 for the other dashed line. And now for the function, it's going to do something like this. Starts out nice and tame as it approaches -4, but now it's approaching its own asymptote, so it's blowing up towards positive infinity. Let me draw it a little bit better. I don't want it to actually touch the dotted line. I just want it to get near as we draw to emphasize that it's moving upwards following the asymptote. On the left, it can do it in a totally symmetric way or in a slightly different way. Just depends on the function we're working with. It has to obey the vertical line test. So if you look really closely, might have broke it right there. Let's draw it so it looks like it really obeys the vertical line test. We want the vertical line test to work because it has to be the graph of a true function. So we're moving upwards the closer and closer we get to -4. If we get towards +5, it's going to do this instead. It's going to drop down rapidly in that way. Toward the right of 5, it could do anything you want. Let's just make it kind of go off like that in a weird pattern. As long as it obeys the vertical line test, it's a true function. Notice it comes in 3 pieces because we made 2 physical barriers cutting up the xy plane. So there's 3 pieces altogether, but this is all one single function, y equals f of x. And for this function, we can now calculate 2 pretty interesting looking limits. I agree, yeah, this one is pretty funky. So let's maybe start with this one. It's going up, so that definitely feels like infinity, right? If we said take the limit as x tends towards -4 for the function f of x, we'll say that this is going to be equal to, well, first visually, it's just blowing up. It's not settling down on any number like 10 or 20. The arrows here are just to give extra emphasis. It's moving upwards in that direction. So we'll just write down equals infinity. You can make the height of this curve as high as you would like by just getting closer and closer to -4. You're like on a roller coaster that's going to send you to the moon, basically, is what it looks like. So that's what an infinite limit is going to look like. Negative infinity just means we're moving downwards, like on this graph. So if we took this one and said, take the limit as x tends towards 5, actually let me move that over just a little bit. Limit as x tends towards 5 of f of x. Well, this time, whichever end we're following, we're going down, down, down towards a negative infinity value, sometimes in weird kind of ways. But in either case, we would say that this one is negative infinity. I feel like I kind of scrunched that in there. Let me see if I can fix it. Equals negative infinity. A little bit better. That might not convert well when it turns into a PDF. Let me just make sure it looks nice. Limit x tends towards 5 of f of x equals negative infinity. So that came from this end of the graph here. Well, any questions at all, folks, on dealing with these so-called infinite limits? Okay, this is a weird topic already in calculus because of what we did in the notation. Infinity, negative infinity, they're not numbers at all. This is just a concept, and the concept is the function gets larger and larger, as large as we would like, by letting x get closer and closer to -4. So we say it's blowing up towards infinity. We're not actually saying that's a number. In fact, this gets even worse. Lim x tends towards a of f of x. Whether it's an infinity that's positive or negative, these limits does not exist. Even though we put down equality and put down a symbol, it didn't mean the limit exists. These are non-existent limits. But what we're saying, however, is that this is in the way the limit failed to exist. The limit of f of x fails to exist because the values never settle down. They're moving up uniformly on both sides. That's a non-existent limit, and this is the information of how it didn't exist. That limit doesn't exist either. Just because we wrote equals doesn't mean it came to a number. That's not a number at all. For any limit to exist, a single-sided, double-sided limit, you've got to put a real physical number there, and we can't. It just keeps getting lower and lower and lower the closer you get to 5. So why do we write this? We're just conveying that's in the way this limit failed to exist as well. But that's another issue in the homework. We cannot put D and E on these because it's true they don't exist, but we need to do a little bit better and say the way in it does not exist. So the answer has to be infinity here. Maybe I shouldn't use yellow, that's already conveyed. The answer has to be infinity on this one. It has to be on negative infinity on this one. If you said does not exist, I mean, that's partially correct, and you would get partial credit for that answer. But the full answer we're expected to show is why it does not exist. Supply the appropriate infinity. Okay, so that's our next concept visually constructed through this graph here. We'll practice it out and then take a look into another exercise. We're nearly done with the notes, but we're not going to try to race through it. If we have to finish this when we come back on Tuesday, that will be okay. We took extra time discussing questions in the class, and that's always a very good use of our time. But any last questions at all, folks, before we take a look into this with more practice? Okay, let's scroll down to take a look into what we have coming up next in the notes. We'll do one of those kind of overall review problems and also tie the dots with vertical asymptotes like we were hinting on the last problem. Then down below, we'll end on an applied setting like this one here. Look into what's going on with the context of drug injections. You'll notice in the reading that there's lots of great applied problems as well. And I'll try to make sure we're always bringing an application at the very end of notes on every single section. I don't think I'll have any exceptions on that because this subject is pretty interesting on its own, taking a look at all the weird things that can happen, but it gets more interesting, more meaningful, and easier to work with and remember if you can put a context behind it. So we'll do that in every single section. Well, at least that's the goal as we go through the course. So first, let's practice this new topic. We have a new definition about vertical asymptotes, again, which was hinted at in our last definition we're looking into. We'll say now the line x equals a will denote a vertical asymptote to the curve y equals f of x if and only if one of the following statements comes out as true. So essentially a vertical asymptote means an infinity comes out one way, shape, or form as an output as x tends towards a on each and every one of those. Whether it tends towards a from the right or the left, or it's a double-sided limit like in our examples, it doesn't matter. You'll still have a vertical asymptote. And if we were heading towards A, x equals A is the equation of that asymptote. So lots going on in this graph right here. It's the function r. That's kind of a weird name for a function, but functions don't have to be f of x, g of x, h of x. It could be r for an r of x function. We'll practice a couple limits, several limits to see how they go. Let's start off with this one. Anyone see the output as x tends towards 2 for the r of x function? Exactly, Emma. This one is going to come out as negative infinity. When we say x tends towards 2, it means we go to the x-axis. If there's an x arrow pointing at a number, that's a good thought. Go to where the x-axis is. Go to around 2, and whether you're to the left or to the right of 2, notice that the curve is plummeting. It's going down. There's no arrows printed, but we'll just take this to mean they gave us the wide enough window on the graph to convey everything we needed to know. It's not turning around. This is a true vertical asymptote right at 2. And because it's going down, this one is a negative infinity. So that's pretty much the name of the game for whenever we get outputs on our limits, infinite limits like these. Same idea with x tends towards 5. If x is getting closer and closer to 5, we're around a vertical asymptote again on this one. But this time it's going up. So this one's going to be a positive infinity. Does that make sense to folks so far on the difference between these two? Awesome. It's good to take a step back and just stare at this and appreciate just how much is going on here. The notation is really, really dense. We're taking a limit, which is a whole new concept about functions. It provides us with a direction, x tends towards 5, provides us with a function, and we have to find some output that comes up with the function values. When we say x tends towards 5, we also have to connect the concept to 5 means a value on the horizontal axis, and we're looking at function values on the curve r of x, which means you're conveying values on the vertical axis, the y-axis. Because we didn't settle down on a number, we said infinity. Lots of stuff is going on here, so it's good to just kind of go slow with these. Read through it in just ordinary words. Don't just look at it. Say to yourself, this is the limit as x tends towards 5 of the function r of x, and it's infinity because the values are getting larger and larger on either side. The more you just kind of think about that, let that soak in, see it from different ways, the better it is to kind of retain all this, because it is overwhelming the amount of dense information we're really looking at here. And with that in mind, it gets even weirder because this one's a single side limit. The rules of multiplication and negative signs do not apply. This is not a negative number times a negative number, because that by the red dot is not a negative sign. That's just a direction. What we're saying is we're heading towards -3, but we're coming in from the left-hand side. And that makes sense why there should be a direction, right? Because if we said limit as x tends towards 3, of r of x, this one's different all of a sudden out of nowhere. This one, absolutely, this one's going to come out as a negative infinity, like you said, because if it's a left-hand limit, we're plummeting down, going down, down, down towards that negative infinity, which means it is a vertical asymptote as well. So negative infinity on this one. But if we wrote this in, limit as x tends towards 3, this one is talking about both directions at the same time. On one end, it's negative infinity, right? But on the other end, as you approach -3 coming in from the right-hand side, like on this limit, it's going upwards. This one's blowing up towards a positive infinity instead. That means if you wrote limit as x tends towards 3, well, I can't necessarily put down one symbol. In our textbook, it's more likely than not, all that they'll put down is does not exist. Other people might write down plus and minus infinity to convey it depends on the direction. But our author often goes just this route. If I can't put down just one exact symbol, positive infinity versus a negative infinity, then the default answer in this scenario is just an overall does not exist. But none of the limits existed. These were just the particular directions they didn't exist. And this one doesn't exist because it blows up in two opposing directions. It's like as bad as possible for an infinite limit in some certain sense. Well, we did it, folks. That's running through limits in this kind of context. The last statement is, states the equations of the vertical asymptotes. But that's what the definition above was all about. The moment you got an infinity statement, whether it's a double-side limit on the first two, or if it's a single-side limit like these, like we had on our last two, if infinity comes up, that means you have a vertical asymptote. And you can really just extract x approaches 2 and just write down. This one had an infinity. Doesn't matter whether it's positive or negative. A vertical asymptote is x equals 2. It has to be a true equation, so the answer isn't 2. Some of our limiting problems will have an answer of y equals 2, so the x equals is important as well. That's got to have an equality because it's also an equation. On this one, when we went towards 5 and got infinity, that means x equals 5 is also a vertical asymptote. I mean, we can see it visually, right? There's the vertical asymptote, x equals 5. But sometimes it's good to think in these terms. What if there was no graph? All you had is the information on the limit. We could still make that conclusion. The vertical asymptote is 5, just by pulling this down to this. Likewise, well, we had -3 and +3. We'll say the last vertical asymptote is x equals, hang on, let me double check. Not x equals 3, but rather x equals -3. We wouldn't put a direction plus or minus on this. We would just write down the number. So x equals a is the number you put down, even if the infinity came from a single side limit like this one or this one. Well, that's a lot of information in one day. And really the great way to learn calculus, if this feels like really, really informationally dense, is recall probably the best way to do class is try to skim this section 2.1 as much as you can before class. Anything you take a look into, even if you're just looking at table of contents or just skimming through, seeing how some of the graphs look, what the definitions are, it's going to kind of preload the ideas in your mind for when you come to class. That makes all this information a lot more sense. It becomes a little bit more sticky. There's a little bit more traction in your brain if you've already just primed what is this section about. Then after getting through the lecture, that's a good time to complete the reading, maybe read at a little bit higher level, and give the homework a try. Then if you do the homework after coming to class, pre-reading, finishing off the reading, then doing the problems at WebAssign, they're going to make so much more sense. You'll probably find that if you work a little bit slower, it's what it feels like we're working slower by doing the reading first, coming to the lecture, participate like folks have been, and then doing the homework, you'll probably find you're going to save time on actually doing the homework because things are just going to click. They're going to make a lot more sense. When a question comes up, you're going to have a targeted question for me, and then my answer is going to make a lot more sense as well. So if you work slower, methodically and in stages, get in a routine and a habit for attacking this course and the material, the homework is going to really be no big deal. There'll be a couple hard problems you might have questions on, but I'll be happy to help out. Well, we still have a minute, but we're not going to ever try to do a problem in one single minute. We'll finish off these notes when we come back on Tuesday. I'll give the due date on WebAssign a 1-week turnaround, so I'll move the due date as appropriate, depending on the pace of the course. But any last questions or comments, folks, before we call it a night today? Okay, well, thanks for your hard work and participation, folks. Recall, this is some pretty weird stuff, but there is an objective here. The main thing that we really want to do is get that slope. And the limiting process turns out to be the tool that we need. So we'll be talking about limits for a little bit while before we turn back to this. But have a great weekend, folks. We'll finish this off, and over the weekend, you'll notice everything starts updating here. I'll move this section down to the next week since we're still working on it in week 2. And I'll be posting the next section as well, both here and on WebAssign. But take care. I'll see you all later. Thanks. Have a good one. Thanks, you too.